Okay, yeah. So, all right. So this is lecture 5, linear regression with basis functions and model selection. So especially now we start to jump into a very important like workflow modules called model selection, and it's coupled with this very simple extension of linear regression, which makes linear regression to be able to work on the nonlinear cases. So everything in the linear regression of basis expansion is the same as linear regression. The only difference is the y. The representation of y is not weighted. If you still remember our nutshell view of linear regression, in the basic linear regression, y is assumed as weighted linear sum of x. And then the only difference now is y is a weighted linear sum of not just xs, but x basis expansions. So this is the equation. I mean, in fact, we just revise from the old x into phi x. That's the only difference. And there's nothing changed at all. Okay, keep that in mind. What I meant, nothing changed at all, is it truly means nothing has changed. The solution is still normal equation based, or gradient descent based, or stochastic gradient descent based. And the model, the parameter are still theta, and it's all the same as the linear regression. The only different part is you revise the x into phi x, and that's it. Okay, let's see more concretely what do I mean about everything is the same, only the basic representation differs. So this linear regression with this nonlinear basis function based formulation helps the linear regression to deal with nonlinear relationships. And very simple, like we can just write out the theta is still just theta 0, theta 1, but we don't write as our old like x, sorry, hope it's not getting crazy. All right, so it's x1, our old x is x1, x2 onto xp, right? Then plus a pseudo feature. But now we just write it as 1 phi x, phi 1x onto phi mx, and then again the transposition is because our default vector is a column vector, and by this way, and it's just showing we are showing a row view of a vector. So this is our normal x view. So this is a nonlinear version before. Linear version before. Yeah. So we covered the linear version. Now we covered this nonlinear version. All right. So the most important point here is the users define the basis function. It's not something magic you learned. It's actually in this, you define it. And for example, just very simple, I just convert my 1x one-dimensional representation into this 1x concatenate with x quadratic. And this is one possible basis representation. Nothing fancy at all. That's it. This is just one possible design, and I prefer it. So very importantly, phi x is predefined by the design person. All right. So now let's see very concretely polynomial basis function based regression. So now I want to show you a code run. So I will stop this share and then go to my other computer. All right, so I think this one is my polynomial regression. Yeah, so I actually share you the link, and this is modified from one of the from this link called it's called Python for Data Science Handbook, and it has a lot of really great notebooks. But it just that version was too long. I modified to be much shorter. So again, so we use like we always try to visualize data, and you actually can directly run this too because I shared to everyone with the link. So we just use random data generation. We generate this data. You can actually tell this is linearly generated. Y equals to 2x minus 5, and this is an error, like can just Gaussian error. So you can just do a scatter plot and plot x and 1, and this is clearly it's generated by linear relationships. And so this is a linear regression. So we actually showed you before, just using the scikit-learn linear regression model. You just fit using that x and y, and then for the future data, in this case, there's a function called link space data. It's a uniform sampling. So you're going to use this in the next next homework. It really just uniformly sample like from that space you specify. Then you use this as your x, and then you try to predict y, and this gives you this y figure, this line. So this is a linear fitting, right? So we understand this very nicely. Let's see now. So this actually plot you the slope and intercept, which is 2 and minus 499. So we actually know this is 2 and minus 5. So it's super good, fits really well. All right, so now let's extend it to basis function based, which in this case is polynomial equation based. To use like polynomial equation based, we need to expand it into polynomial features. So again, this is U design. So in this one, it's actually super simple. This has a specific function called polynomial features, and this is in the pre-processing module. So you can think about this as feature engineering. So as a designer, you are designing the features. In this case, is I think it's quadratic, cubic, and also power 4. Actually, no, it's just yeah, it is 3, 4, 8. Yeah. You generate actually the polynomial features. So you have your 2, 3, 4 is your input data. You generate like quadratic like polynomial 1 term, polynomial 2 term, and polynomial 3 term. And this is a very simple function. And then, okay, so this is what? So this is trying to show you, you just use this polynomial function, a polynomial feature function, to recreate your original x features. Then everything else is the same as the linear regression. So this use the pipeline, which is the linear regression pipeline, by only just changing the features into polynomial features defined by a degree parameter. The default is 2. I hope this, just think about everything's fixed using the linear regression. I only just change the feature from x to phi x. Yeah, so that's really about it really is. So this step, just everything is the same, but change x to phi x is the polynomial case. Then just use totally the same linear regressions fit, really linear regressions predict function. All right. So let's generate this data. So this is actually, it's just a data generation. You can dig in to see how to generate it. It's actually 1/x function, but yeah, anyway. So you can, it's not linear at all. I need to, there has to be some kind of nonlinear function to fit it. So here, and you just vary using, again, totally the same as linear regression, but change the feature by that degree parameter again. So let's go back to see here. Everything's the same as linear regression. The only differences is this polynomial feature function will convert x to phi x. And there's a parameter is degree. So when degree equals to 2, you are generating polynomial 2 features. When degree equal to 3, it's 3 polynomial 3 features. Okay, so let me actually do a little bit change here. So I have 4, right? Let me do 3, 5, maybe 7. Let's see what do I get. All right, so when I'm using polynomial 1, so x is phi x is actually x. It gives me a linear line, right? That's exactly giving me a linear line. When I'm using polynomial 3, it changes from the x into like x quadratic and x cubed. And this is how it gets. This is the orange line. When x equals to 5, I just keep adding, it's like x4, x5, and then, so that polynomial feature just change x to phi x. And then everything else is the linear regression, fit function, predict function, totally the same. And this is how it gives you much more nonlinear regression fit. All right, I hope this is good. Let's come back to the slides. Okay, we'll come back to slides. Do this. All right, so yeah, we are here. Okay, so I think this gives you a good overview of what polynomial regression is. It's really just x changed to phi x. Everything's the same as linear regression. And more visually, it's just a linear line. If you add x quadratic term, it will become a quadratic line. And but you do the same. I mean, in the linear case, you do x transposition x inverse x transposition y to get the fit line. And in the polynomial case, you do the same thing, but just change the x into phi transposition phi, take inverse phi transposition y. That phi is just this vector representation. It's really feature engineering. You engineer the feature. All right. Okay, so I think this page initially want to derive this, but I think we're good. So so this x representation in this norm equation, we actually know it's a tabular n times p view, right? Let's actually show this. So this is like sample 1, first my first sample, second sample onto the nth sample, and the feature is like this 1 to p. I always abuse it. Actually, if I have x1 to xp plus a pseudo feature, the whole thing should be xp plus 1. Yeah. All right, so can you tell me what is the size of the phi matrix when considering all the, because it's also a matrix, right? What is the size of the phi matrix? Assuming the size of phi is 1, 2, onto m. What is this phi x matrix size? Let me see the chat. Yes, it's n times m. Yeah, so this is actually, again, my sample size doesn't change at all. It's still sample 1, sample 2 until sample n, and the only differences is just the features change to from the original 1 to p and then to my current 1 to m. And this means what? My theta size is in the, sorry, there's a little, my theta size actually is, so now the number of parameters need to estimate needs to be the same size as the phi. And this is actually totally just derive, you can derive this. So like this is m times n, n times m, m times n, n times 1, and then just do a calculation. What you're going to get is m times 1. It's m times 1 vector. All right, so the number of parameters is the size of your basis feature representation. All right, so again, visually, if you the two-dimensional case, we show you the one-dimensional. So previously we fit a line, and also in the two-dimensional case we fit a hyperplane, right? So when we add the quadratic term, we actually fit we fit like a surface, a bowl shape. So it's not a hyperplane anymore. It's not a hyperplane. It's quadratic valley shape. Yeah. A mountain shape in this case. Yeah, mountain shape. So when the basis function are given, the problem of learning the parameter from data is still a linear regression task. Okay, so I already showed you this, and then let's just go over a little bit careful one more time. So again, so you have a little understanding of each of the bases, how they look like. It's actually good, help you understand. So the quadratic 2 term, quadratic 4 term, and not quadratic, power 4, power 6, they are all the U shape, right? Of course they are U shape, right? They're totally positive. And then going this, it's the difference is just they're going sharp, very quickly up, or going a little bit like, slower up. And this is the even case. The odd case, it's always like a tilted S shape, and then in the extreme case, it becomes the linear line, right? That's really the extreme case. And the cube and power 4, power 5, and this can help you to understand when your largest degree here is 7. So be again mindful when I'm saying degree equal to 7. It doesn't mean there's only x power of 7. It means what? It means this basic term has 1 x quadratic on 2x7. So, and actually you can tell, I mean, in those points, I don't have a training point, and this x7 kind of dominated in this extrapolation, the regions. I mean, the x7 kind of dominated in the last, which it's very questionable. Is this a good thing or bad thing? Is this generalized well, or is this generalized badly? Will this really hard dropping of this x7 controlling everything beyond the right, is that a good one or a bad one, right? So which degree should I pick? How to pick it? And this is because like I told you, right? Everything is you design it, you control. But how? So this is exactly a very important module called model selection, and we're going to talk about later in the next. So I think I cannot finish about other basis function. Let me just do a quick this. So there are many other possible basis function, not just the polynomial, and there are also something called a radial basis function, sigmoid function, spine, B-spine, Fourier basis function, wavelet basis function. There are just really many kinds. It's just a design, it's your choice. And then you try to do that linear summation of all the different bases to fit your data. So I think I will shift it to next time. So let's just stop here. So there are many basis functions. We will cover a little bit about RBF or Gaussian basis function next time. And this is all for today.